Questions? As far as that goes, I mean, one year the class used to ask me these questions. They had a class over mechanical engineering. I'd say, I'd answer any questions that they wanted if I could, and I found they were asking me their homework problems from this other class. It took me about 3 questions, 3 days before I started saying, gee, these questions sound like, they're coming from some other course. Anyway, so if you got any other questions? Okay, we got everybody. So let's go ahead and start. Today is the 27th. I'll be gone tomorrow. 29th and 30th we'll have class, and we should finish up on the 6th. Nothing happens, and I don't think anything's going to happen between now and then. Nobody does anything important. Everybody's on vacation over the 4th, right? So, last time we talked about adhesive bonding, and I talked about type 1, which basically was a surface tension, and I haven't gone through all the stuff on surface tension I want to, but just a liquid between 2 flat plates, and I brought in the Johansson blocks, and you can see how you get some adhesion there. And then we talked about the kinetics, which is the Stefan equation. Same guy as Stefan Boltzmann, radiation law, basically a physicist, says that the pressure that you apply, this is between a liquid between a viscous liquid between 2 plates, and you're trying to squeeze the plates together with a certain pressure times the time, so it's a kinetic equation, revolving times 3/4 a squared, where it's the radius of a disc. If you go to Bickerman's book, and by the way, I went online yesterday to Amazon. It's amazing what you can find on the web. And there's a second edition of Bickerman. I didn't even know it existed, from 1968, and I bought it for $100. How about that? Anyway, viscosity, and 1 over the final thickness of this between the plates squared minus 1 over the initial thickness squared. And basically, usually this one kind of goes to 0, because if there's a difference, this is just some stuff that actually came right out of Bickerman. I guess I can put light on that. So if I'm using kind of 1 atmosphere pressure, and I have a viscosity like water, and I got a disc, that's the radius of the disc, so it's a 2 centimeter disc, so 3/4 inch, kind of a little bit larger than a quarter. And it starts out 1/10 of a centimeter is 4 mil thickness of liquid, and I want to go down to 4/10,000ths thickness. That'll take 7.5 milliseconds, just because of the resistance of the viscous liquid. Okay, that's not very long. That may be all the time I have if I'm trying to put labels on glass beer bottles. So I'm needing an adhesive, very low viscosity, in order to slap those labels on the beer bottles. If I go down to 1/10 of an atmosphere and go up in viscosity, 10 is something sort of like maple syrup or something. Okay, it's not a very thick, or it's thick, but not thicker than water, but it's not terribly thick. And you go to a much larger diameter disc, and so now I'm trying to bond a fairly large area and spread it out, and it takes a lot of time. Okay, depending on how thick or thin I want to go. If I want to go really thin and get a stronger joint, I could be sitting there for hours. And we talked about the fact that if you got something bonded to the wall adhesively and it falls off, what do? You go up there and you push it on harder. All you're doing is trying to increase the force so that it'll stay there for a longer period of time. Okay, and we all know that if I contaminate the surface, then I'm not going to get as good a bond, because basically the stuff doesn't wet it. In any case, that gives you some sort of feel for the time to make a bond. But if you start looking at these times, sort of how long a bond would last, and you start realizing that you can change the viscosity, and we didn't go through it. I know you all like differential equations, but I only saw 1 differential equation in this course, and I said that's just to prove that I'm an MIT professor. But there is a differential equation that is where the Stefan equation came from. But if you solve the equation, you can go in reverse. So if I take those Johansson blocks and I want to pull them apart, or if I just want to hold them there and I want to predict how long they will last, I can slide them together, get a nice thin joint, and I could use the viscosity of that oil and I might find those Johansson blocks might stay together, hanging there, depending on the weight of the block, which is in this case going to be related to the pressure of separation, right? And I used the 3-inch long Johansson blocks to show you that they'll hold a substantial force. There's no big deal sliding two things together. If one of them's a 1/4 inch of steel, thick steel, that's not very impressive. But when you see it, that little thin film of oil hold a 3-inch thick piece of steel, it's sort of impressive, right? But how long will it hold it? Well, I've held them before, and they might last 60 seconds. They might last 100 seconds. Because this Stefan equation, if you go back through the differential equation, works in reverse too. Okay? It works for flattening out that film of adhesive, but it also works for bringing it back together as a ball, in a sense. So it turns out this equation tells us what we need to do to make an adhesive joint quickly, but it also tells us what to do if we want an adhesive joint to last a long time. If we can try to make it thinner and thinner and squeeze harder on the wall, but that only goes as 1 over the thickness squared with the pressure or the time that we're squeezing it. However, I started talking at the end of the day about I can change the viscosity by 10 orders of magnitude by just causing that liquid to become a solid. Okay? Maybe 15 orders of magnitude, depending on how good a solid I make it. Okay? Well, if I change these times to 15 orders of magnitude, for all intents and purposes, that's an adhesive joint that, unless I got very, very high pressure stresses on it, it's not going to pull itself apart. Okay? So an adhesive, basically, in most cases, is something, unless I'm talking about tacky adhesive like Scotch tape, which we can talk about in a second. An adhesive generally is something that I want to have low viscosity when I make the joint, so I can get a thin joint, gives me reasonable strength, and then I want to harden up that adhesive by some technique. And there's 3 ways, basically, to harden up something that's liquid. You might think of the 3 ways to do it?
Yeah, I'm guessing, I don't know. That's right. I'm thinking like simple, like an Elmer's glue or something like that. It's just as moisture kind of dries and it becomes
exactly.
That's right.
Yeah.
Then the other one I would think would be like an epoxy. You mix 2 chemicals together, and there's a chemical reaction that actually makes them harder.
Yeah.
And then
so the first one is solvent removal. Okay. The water evaporates away. Okay. It's the solvent that made it a liquid. And if I evaporate away the solvent, Elmer's glue, sniff the glue, get high, and I'm left with the plastic that solidifies. Right? So solvent removal, then there's chemical reaction. There's another one. What happens to water if you go to the Arctic? Yeah, solidification we call it. Turns to ice. Okay? Ice is a better adhesive than water. In terms of once you've made it. So the 3 techniques are solvent removal, chemical reaction, and solidification. The simplest solvent removal is none other than a postage stamp. Okay? It's got, this kind of adhesive on the back. Well, nowadays, postage stamps nowadays are self-adhesive. And you don't have, but the old days you had to lick a postage stamp. Or take an envelope. You still have to lick it, right? And what are you doing? You're adding the solvent to turn your glue into a liquid. And then what happens to that liquid? Paper is porous. It kind of diffuses away. And then it, eventually vaporizes, and it dries up in the air. Unless you're in New England this time of year, where it's, constantly raining, but no water evaporates. But solvent removal, Elmer's glue, okay? Airplane glue. Airplane glue, we're using some sort of xylene, or I don't know what it is, some hydrocarbon solvent, right? But you can use water as a solvent. Elmer's glue, the paste you used, when you used it in 2nd grade, making glue and eat it, that was water, right? And you can loosen it up by adding more water, right? You open one of those things and you see it dry out. Rubber cement. Okay, rubber cement. It's got a solvent in it. You leave the cap off and it solidifies, right? So you mentioned epoxy is a good example of a chemical reaction. I actually have a chemical reaction, and the thing goes from liquid to solid because of the chemical reaction. Anybody think of any other chemical reaction in adhesives that you know about? Yeah.
High solids paint.
High solids paint. Is high solids paint a chemical reaction? Okay, I don't know high solids paint. I mean,
It's a two-part mix.
oh, okay. It was two-part mix. It's a chemical reaction. Old epoxy paints were chemical reactions. Okay. Most of the paint, you go buy latex paint at the hardware store, solvent removal. Okay. Once the water dries, you know, it solidifies. If you talk about an oil-based paint, once the linseed oil evaporates away, you know, it solidifies. But an epoxy or a solids paint, there's another, yeah.
What about like super glue where it actually melts the plastics together?
Ah, super glue. There are some glues, like if I wanted to take two pieces of plexiglass and bond them together, Brian knows about this, he learned about this. You can take chloroform and you can put 1 drop of chloroform on there and it actually dissolves the plastics. And then when the chloroform evaporates, it's a solvent removal, and then it solidifies. And you've actually welded the plexiglass together. So that's a solvent removal. A chemical reaction, if you're talking super glue is a chemical reaction, but it's a polymerization, just like epoxy. I basically take a liquid, but what's the second? Anybody know with super glue, you just put one liquid on there and it sort of hardens up. Anybody know what the second component is for super glue? Pardon?
Moisture from the air.
It is actually hydroxyl radicals, which is in moisture. So in a sense, it's not as a moisture from the air, but it's for a super glue, or what we call super glue, is actually a cyanoacrylate. Okay, and actually, cyanoacrylates were discovered by serendipity, like in 1956. Some guy was trying to make new polymers, and he found that he was gluing things, the glassware and stuff, in his lab together, and he said, this is interesting. So let's see, 116 line here talks about cyanoacrylates. They obviously have cyanides in them, but anyway. The unique adhesive activity of the alkyl 2 cyanoacrylates was discovered more than 20 years ago. Well, this book is old. It's the second edition. This book is 1977, so 20 years before, in the 50s. During a routine measurement of the refractive index of a freshly prepared cyanoacrylate sample, the prisms of the refractometer were adhered. Okay. Within a few hours, the full implication of these inseparable prisms was apparent to scientists using the cyanoacrylate to form strong bonds between a variety of substrates. This marked the beginning of the development of the adhesives. So it was sort of a mistake. They're just trying to make new types of polymers. And as they went into it, they found you actually get a polymerization reaction that's catalyzed by hydroxyl radicals. And one of the reasons you can glue your fingers together so well with super glue is your skin is slightly basic. If you measure the pH of your skin, it's like pH 8 or 9. So it's got good hydroxyl radicals. Anybody try to use super glue on wood? Doesn't work so well, does it? Wood is slightly acidic. Doesn't have as many OHs. So if you want to take some lye, some sodium hydroxide, and paint your wood, let it dry. So now it's got some hydroxyl radicals. You use the super glue to bond like mad, okay? Because it's got lots of hydroxyl radicals. So super glue, yeah, you can say some moisture in the air, but the moisture in the air is what gives you your OH bonds, which is the catalyst. Just like in epoxy, you have a catalyst that starts the polymerization reaction. OHs are everywhere, and that's why super glue works on so many things. Other adhesives you can think of. What about your anaerobics? Anybody ever used Loctite? Okay, what's Loctite? Okay, Loctite is an anaerobic adhesive. Anybody know what aerobics is? It's exercising, right? It means getting lots of oxygen. Okay? What's anaerobic? Without oxygen. It turns out the anaerobic adhesive is a single liquid, and if you look very carefully at the tube or the can of Loctite, you'll find that somewhere they've introduced a hole so air can get in there. And when you put that little grip of Loctite on a screw down inside a thread, there's no air in there, down inside the threads. And so it hardens up without the presence of oxygen. Okay? It's an anaerobic adhesive. And it made a multi-billion-dollar corporation. It's like one of my favorite stories. A guy was he didn't get hurt that badly. He was on a cherry picker. Okay? He was working, on transformers and stuff. And the lower mount to the hydraulic piston that raised the arm up and down had broken. And so I was asked to come in and figure out why this thing broke. And it's this one company down south of here, down in Taunton, had repaired this thing. And they had gone by the manual. It says use Loctite on the bolts. I mean, clearly the bolt that held the clevis for the bottom of this hydraulic cylinder, the bolt had slipped out, the clevis came loose and it dropped down, and he's up there in the cherry picker, and the cherry picker drops immediately 3 feet. And he kind of, he says he's got a back that's terrible, will never work again, but actually he did get hurt that badly. Anyway, but the bolt came loose. And it said use Loctite. And the mechanic did. Okay? He used Loctite. Well, Loctite's a big corporation. And not everything they make is an adhesive. And not everything they make is to make bolts or keep the nuts from backing off the bolts. And so he went and he got some Loctite off the shelf, except this was Loctite anti-seize compound. Okay? This was a lubricant, not an adhesive. Because I went and I analyzed it and it had a bunch of zinc sulfate in it, or zinc sulfide. We looked at it kind of looked greasy to me, it didn't look hard. So I just took a little sample of it and analyzed it with zinc sulfate. And it turns out zinc sulfate is one of the compounds you put in anti-seize greases. Okay? It basically contaminates the surface really well so that they won't seize together. So rather than putting something on to keep the nut from backing off, he put something on there that would help it back off. Okay, but it said, the instruction manual said Loctite, it didn't say what type of Loctite. So, I always thought that was kind of a clever little thing, how you should write the manuals. Although, speaking of writing manuals, since you're all government employees, one of my favorite stories, the Watertown Arsenal over here is now a mall, but before it was a mall for 150 years, it was actually an arsenal where they actually made cannonballs and cannons and other stuff. And I had a student who worked there doing his thesis back in the mid-'80s, and there's a story they ordered this is how you write things. They ordered a rug for the conference room, okay, and the purchase order that the government put out for a bid, competitive bid contract said provide rug and rug pad and install rug. And the winning bidder, what did he do? He installed the rug, and the rug pad was rolled up on top, sitting on top. The purchase order didn't say install the rug pad, just said provide it, right? And he figured he could save that money and he could underbid everybody else by reading the contract very, very carefully, okay? And guess what? The purchasing department over here at Watertown Arsenal backed up the contractor, and when the people who had ordered it complained and said, we wanted the rug pad, and underneath the rug installed, and this guy didn't do it, they went back and looked at what they had written on the purchase order, and the guy had done exactly what the purchase order said. And they had to issue a new purchase order to remove the rug, install the rug pad, and then put the rug back on.
Did you get it?
Yeah.
Did you get the next one?
I don't know if you got the next one, but nonetheless, this kind of tells you the story here. Industry wouldn't have stood for that, but, I guess the government goes by the book sometimes, right? Okay, so we talked about several solvent removal, chemical reactions, solidification. What type of solidification glues can you think of?
hot melt adhesives? You know, little glue guns?
You take this, huh?
Liquid nail.
Liquid nail. Actually, I haven't used liquid nails, but I thought that was just a liquid you poured on.
No, it's a caulking.
Oh, it's a
gun,
caulking
and
thing?
you put it between two boards, and then they use it for other stuff. But
That sounds to me like a solvent removal, because you're just putting it in there. You're not heating it up. Solidification usually involves a temperature change. Okay.
Gorilla glue, what's that do?
Pardon?
Gorilla glue?
Gorilla glue is nothing more than the old Elmer's glue, super Elmer's glue, solvent removal. I think liquid nail and Gorilla glue are basically water-based adhesives. And wood, hot wood, if it's nice and dry, will soak up water out of those adhesives. If you have wet wood, it's not going to glue very well. Okay. But solidification of hot melt adhesives. You got a glue gun, a little hot melt glue gun. You heat it up, put the glue on, burn your fingers. You know, it solidifies, it hardens up. Right? What's another one? You drove on it. You rode on it as you came here today. Asphalt. Right? It's a hot melt adhesive. You mix it with gravel and you pave roads. Right? Heat it up, cool it down, turns to a solid, holds those rocks together, right? Right? So, industrially, we use a lot more hot melts than we do in our homes, just because we don't have ways to heat things up, or people burn themselves when they heat them up. But industrially, they might use a lot more solidification, phase change. Yeah.
How about like powder coating paint?
Powder coating paint. That's a good industrial example. In fact, when whoever it was that mentioned the paint before, I was about to say, but I was going to wait until we got to solidification. But powder coated paint, you have these little particles of plastic, and you basically heat them up and shoot them as a liquid at the surface. And when it cools down, I've just plastic coated the surface. I mean, if I look at outdoor furniture now, it'll have a 1/2 to 3/4 of a millimeter thick layer on good stuff of powder coated paint. You're basically just shooting a plastic at the surface. It can be polyethylene at 250 degrees Fahrenheit. In the powder form, and you have a gun that'll heat it up and keep it from turning to a ball of liquid. You got to keep it as a powder, and then so it'll be particles. That's the trick of the powder coating. Okay. The adhesive there is basically just solidification, so that's a good example. That's probably one of the largest examples right now. I mean, people all over the world are going to powder coated paint. No environmental problems. I mean, one of the problems with solvent removal is nobody wants to use anything that's volatile organic compounds because of the EPA anymore. Okay, petroleum distillates getting into the air. Well, that would be horrible. That's why we should cut down all the pine forests in Georgia and Tennessee, because they're giving off, those trees are giving off petroleum distillates like mad. Okay, where do you think rosin comes from? Okay, and those trees are giving it off. But we're not allowed to. I mean, actually, we are allowed, but you have to have big extractors to recover it. It's actually getting to the point where those solvents are worth money, and you don't want to just blow them up in the air. Okay, and they also contribute to global warming. But industry has, in the last 20 years, because the EPA has switched over on solvent removal to go on more and more water-based solvents. And it's sort of interesting because chemists are developing water-based adhesives for things like coating paper, that when the water evaporates, what the adhesive that's left behind is water resistant. Okay? And the way you do that is you end up making complex molecules that will have several different ends, if you will. And actually, typically what people show is a polar end and a non-polar backbone. And this is kind of how people often show a stearate molecule, a soap molecule. One end is polar, and the other end is this long chain polymer, which is basically just a series of carbons and carbon backbone chain. It may be more complex, but polyethylene is basically just a bunch of carbons and hydrogens. Okay, and so stearate has 22 carbons, and oleates have like 12 carbons. And if you go to the organic chemistry, that they have different greases and oils that come from certain plants. I can't remember what the Greek word for lamb is, but anyway, if you if you go back and look at some of these Greek lambs, lamb fat, grease, it turns lamb has a certain number, like I don't know if it's 14 or 16 of these carbons. And that's the type of grease, and the type of grease is not stearate, it's not oleate, it's something else, but it comes from the root word for lamb, because that's the type of grease that comes from lamb, okay? But anyway, this is a question of how many carbons. This is a non-polar end. This is a polar end. The polar end will dissolve in water. The non-polar end will not. So if you're clever about things, you may be able to dissolve it in water. When you take the water away, maybe you can get a chemical reaction that eliminates the polar ends, and now the stuff won't dissolve in water. So the chemists do some pretty neat tricks. And that's because they want to be able to put it on with a nice water-based solvent that's environmentally sound, but then they don't want it to dissolve away in water. After all, if we're going to make plywood, there's interior grade and exterior grade plywood, right? Well, that's just the glue. You're gluing wood. Interior grade, they're going to use a water-based solvent because you don't worry about it raining indoors. Exterior grade, you got to use a water-insoluble glue because it's going to rain on it, right? That's the difference. And you pay more for exterior grade than interior grade because there's a whole host of glues. Glues come in all kinds of shapes and forms. And in fact, that's what most of this book on Handbook of Adhesives is. If you go to the section B on adhesive materials, so the first part is Introduction to Adhesives, and chapter 3 is include. That's the one by Zisman that I handed out. It talks about type 1 bonding and mechanical interlocking. Animal glues. Okay, the old story of sending the horse to the glue factory. All they want is protein. Okay, the proteins have these type of polar and non-polar ends, and they make pretty good adhesives. Fish glues. Okay, anybody know what Gurry is? G-U-R-R-Y. You got to go to an unabridged dictionary. This is actually has been an important thing in Massachusetts. But Gurry is fishing offal. What's offal? It's the leftover stuff. I mean, chitlins are offal from pigs and stuff, right? If you're from the, have you ever had chitlins? Some of you have had chitlins. You ever had fried chitlins? Chitlins is really good. Haven't had bacon, but the boiled chitlins, well, that's sort of like smelling something that you just want to flush out the toilet. Anyway, fishing offal. This is old fish heads and fish backbones after they filleted the fish. Okay, but there's actually a use for it to make fish glue, or a slimy gummy substance is the second name. So Gurry, and I always like to tell the story, is we talked about postage stamps, and I can remember back 20-25 years ago. I don't know if it's really true anymore. I don't do it anymore, but I can remember paying my tax bills, and Massachusetts will give you a envelope to send your taxes back in. Now I do it electronically, but back in the days when you had to use postage stamps and stuff, I can remember licking the edge of that Massachusetts envelope, and it was one of the worst tasting things in my life. I did it for about 2 years. In the third year, I remembered, and I just got a wet sponge, and I wet it with a wet sponge rather than licking it with my tongue. And I'm convinced that Massachusetts was using Gurry or fish glue because it's an industry in Massachusetts. I mean, we have a fishing industry, and I bet they were supporting it and getting their envelopes probably made with Gurry, and it tasted terrible. So it was adding insult to injury. You had to pay taxes in Massachusetts, for which you get nothing, and you get nothing in return, and you have it leaves a bad taste in your mouth. Okay? Anyway, so there are animal glues, fish pet glues, casein glues, and adhesives. What's casein? Anybody know what it is? Casein is basically milk solids. And casein glue, if you actually go to that chapter here, animal glues, basically says almost any type of protein constituent of animal skins, connective tissue, and bones, basically collagen. And here's the formula for some of these hydrolyzed collagen. Okay, so that's animal glues. If I go over here to fish glues, What's it say about fish glues? Was the first glue liquid that reached commercial importance and was the forerunner of all household glues. How about that? And it tells you about the unique qualities of fish glue. One, it's completely water soluble, so if you want to make, can be made water resistant and insoluble in water by a chemical reaction. But one of the other advantages is it's very water soluble. So if you are doing some manufacturing, you want to glue something together and then have it, take it apart, you can just dip it in water and the glue will come apart. Casein, the problem with casein is manufactured from skim milk is a byproduct of the dairy industry and subject to the economics of that industry. It turns out, with spray dryers to make non-fat milk and stuff, we don't use a lot of casein anymore because it's more valuable to sell as powdered milk. Okay, most of our casein comes from places like Australia and New Zealand now, and Argentina, because they got lots of milk. Okay, more than they can take care of there. And it turns out the equipment to make casein glues is less expensive than to make skim milk. So basically, casein glues, soybean glues, blood glues, starch-based adhesives, cornstarch, okay, or wheat starch. Virtually any organic product, whether it be edible or vegetable, here you can see forms proteins or starches that have these kind of polar, non-polar molecules. And most of these things are water soluble, and they tend to be, when you're just using old blood, there's lots of, in the slaughterhouse, there's plenty of old blood around. In fact, if you don't make it into glue, you're going to have to pay somebody to get rid of it, right? So you might as well make it into a saleable byproduct rather than paying to get rid of it. So most of these glues, old fish heads and whatnot, are fairly inexpensive. We're talking about things that cost anywhere from 10 cents to 50 cents a pound for these types of glues. Pretty cheap. But if you get down into the next thing that you go through is a bunch of the rubbers. These are the tacky things like Scotch tape or Post-it notes. Okay, just Post-it note. It's got these adhesives actually have tack to them, which is another property of adhesives. And tackiness is because they actually put rubber particles in there, and the rubber particles actually will stretch. They're mixed in with another adhesive, and they're soft enough rubber so that when you try to pull them apart, if you look at a microscope, you can actually see these little stretchy things. In fact, I used to do it when I was in high school or even at MIT in class. I'd be bored and I'd have a little piece of Scotch tape, and you just make a little U shape on the Scotch tape, and you keep on putting it back and forth, and the adhesive is sticking to itself. And eventually you get to the point, and you can actually see the ligaments. As you pull that thing apart, you can see the ligaments of rubber that are stretching that give it tackiness. So when you do a peel test on a tacky adhesive, a peel test is something like, you got something shaped like this, and I'm going to pull it apart, then I will actually have little ligaments. And here's my glue back here, and I've got coiled up little things of rubber, and as I pull it apart, those coils of rubber get stretched out and actually hold the thing together, and it gives me my tackiness to my adhesive. And so that's why Scotch tape works. Okay? There's another little trick on Post-it notes. Unfortunately, I don't know if it's because my secretary buys the off-brand. Oh, this is a real Post-it note. She buys an off-brand because it's cheaper. But I did bring one of these, a clear Post-it, and a 5x magnifier. If you look very carefully here, although it helps to get some dirt and dust on it, it's not hard to find at MIT. Okay. There's a lot up here. I may have too much now. I don't know, I may have screwed it up. Probably screwed it up. But if you take a Post-it note and you look very carefully, I don't know if you'll be able to see it. I'll pass it around and you can try it. You'll see it's kind of like a dried riverbed where the glue is. I can remember 20 years ago, I took a Post-it note sitting in a class or a lecture somewhere, and I was bored to death, and I just kept on putting it back and forth on something and getting the adhesive dirty. And I saw this little pattern of dots. And the original Post-it notes, if I had some vintage Post-it notes, they actually put the adhesive on only in certain dots. You didn't want 100% adhesive on the Post-it note. If you had 100% adhesive and you try to pull that thing apart, you'd rip your paper. The joint, you got so much bonded area that you would rip the paper. So one of the tricks in adhesive in Post-it notes is to only have adhesive over about 50% of that surface. And so that you have little spots. Now, what they've done, and I've been checking the last couple of days in both these and Post-its and the non-Post-its and dirtying them up with dust to see things, they now have something where I'm sure they basically have some sort of water-based system that when it's a two-phase system and it kind of leaves something just like a dried riverbed. And so you have little areas, but they're not nice little dots. When I looked at this 20 years ago and discovered at that time they were printing dots of adhesive on the back of the Post-it note. Okay? Nowadays they're clearly just putting a layer of something on there and letting the whole film dry up, but they've designed the film in a way that when it dries up it leaves little islands of adhesive that are not regular.
When is it dry? You put it on the wall?
No, it dries at the plant.
Yeah, that's right.
Okay? When they put it on in the film coating line at the plant, they got a dryer that sucker water off or whatever. Okay, and when you get it, it's got a tacky little rubber adhesive on there that is not going to dry, at least not for a certain number of years. Think of Scotch tape. Scotch tape has got they put it on there with some sort of solvent. They probably heat it up a little bit to get some of the solvent off. They leave behind these little rubber islands of these tacky adhesives. But if you don't use that Scotch tape for 10 or 20 years, you try to pull that apart. You can't get it apart. What happened? The solvent diffused out, hardened up, and I got a much stronger bond than I ever wanted.
So what's the method of adhesing with a Post-it on the wall? It's not.
The Post-it is actually a tacky adhesive, okay? But the tacky adhesive really doesn't, you're not doing anything to change your viscosity on that tacky adhesive, okay? If you put it on with a certain thickness or a certain force time product, it actually doesn't have particularly great strength. But when you try to peel it off, it appears to have greater strength because you're stretching out all these coiled up rubber molecules. If you're doing it in a peeling mode of failure as opposed to straight tension, okay, you actually uncoil these guys, and as you uncoil these guys, you're doing force through a distance. And it takes more work to take it off. When you put it together, the coils are all coiled up. The springs are all coiled up. When you pull it apart, you have to break each one of those springs. So a tacky adhesive appears to have greater strength, actually does have greater strength. It takes more force to pull it apart because you got to stretch out each one of those springs before it snaps. So it takes more force to take it off than put it on. But in fact, it's not getting the greater strength because of the change in viscosity. Okay, there's no change in viscosity with the Scotch tape. Okay, but there is a uncoiling of these little rubber chains. Okay, so a tacky adhesive, which is most of these little rubber adhesives in here, is a different animal than what we've been talking about. Okay, it's kind of in a class by itself. And then you get down here and you get into all kinds of fancy, specially made polymers that are made in some chemical plant, and you'll see the cyanoacrylates, the crazy glue, it's up in here somewhere. No cyanoacrylates is on. It's at the top. Cyanoacrylates, chapter 34. That's your crazy glues or your super glues. Anaerobic adhesives, the second one there is the Loctites, acrylics and sealants, polyamides. Now, once I start getting to, I told you that the starch-based stuff, the stuff I buy at the slaughterhouse or the old wheat stalks or corn stalks, the stuff that ordinarily I would feed to the pigs, but I'm going to make starch glue out of it, that's 10 to 50 cents a pound. If I want to do some fancy processing on that stuff and change it chemically, it might get up to $1 a pound, but it's still water-based. If I want to get some things that are oil-based, based on digging oil out of the ground, I'm going to be starting to talk prices that are on the order of $2 a pound. Because let's face it, paying They got to do all this processing in the chemical plant. And if I get really fancy, like some of the polyamides, which have high temperature capability, very resistant to all kinds of other solvents, I might be talking $400 to $500 a pound. And typically, if I'm trying to build an aircraft, I'm Boeing, I'll be spending $400 a pound for my adhesives, because those adhesives have to last for 30 or 40 years. The biggest problem with adhesives, the cheap adhesives, the glues and starches, the animal glues and the starches, vegetable starches and stuff, is that they can be attacked by water. They're organics, they degrade. Bugs will eat them, okay, over time. And so it turns out when the steel industry, not the steel industry, the auto industry, after the '73 oil embargo, and most of you weren't even alive back then, okay, as I think back to these things, but some of you might have been born, okay, barely. I guess a couple of you were still running around in diapers or something. But in any case, '73 oil embargo, before that time, if you ask your parents, you'll find that people only expected a car to last 3 or 4 years. And the warranties may only be 2 years. After the '73 oil embargo, and I've never quite figured out the reason, but everybody decided cars should last 7 years. Well, now people expect cars to last 10 or 15 years. Okay? Back when I grew up in the old days, when you had to walk uphill both ways to school, a 25-year-old car was a big deal. You'd only find them in Arizona or California because, in New England and someplace like that, they just rust out in 3 years. They actually show rust in 3 years. Well, people in like '75 decided, well, I want a car to last 5 years if I'm going to pay all this money for gasoline. And so they started having 5-year warranties on the car, and then they started having 7-year rust-through warranties. And they got that because they went to galvanized steel. The problem is they didn't know how to weld galvanized steel, and in the late '70s and early '80s they had some serious problems in Detroit with the quality of the welds through galvanized steel. They knew how to weld bare steel, but they didn't know how to weld galvanized steel. And they started looking in the early '80s at more and more adhesive bonding. And so things like the door frame, the early Chrysler minivans, the door frame, you have an inner panel and an outer panel. The outer panel is the steel panel that you paint on the outside, and that's the outside of your door. The inner panel is the one you cover with plastic or whatever, and the handle on the inside goes, you close the door with and stuff. And they started, they make a hem flange. They basically put the outer panel like this, and the inner panel kind of wraps around, or the outer panel wraps around the inner panel like this. But in order to do that, they needed something so it wouldn't rattle around. And so they started putting sealant sort of glues in there. And typical automotive industry, they were using cheap $1 a pound glues made from these starch-based products. And within 5 years, people had doors rattling because the adhesives just were attacked by the moisture in the air. And 5 years later, you had nothing gluing your inner and outer panel together. You had the hem flange mechanically holding it together, but it was just rattling in there. Okay, and in accidents, those doors would just fall apart and things like that. Today, the automotive industry uses $15 a pound adhesives. And for them, for someone who has selling a vehicle that's, where $2 a pound is about what you can afford to pay for things on average, to pay a $15 a pound penalty for something that goes into the structure, gluing the structure of the car together, it's because you really need the properties, the moisture-resistant properties, so that those glues will last 10 years or 15 years. And they still, hem flange, bend the flange over, don't weld it, but seal it with this caulk on the doors of these things. But they're using a much better glue. And Boeing has to go and spend, on very fancy adhesives, spend $400 a pound on the adhesives they use. Okay? So, what else do we want to say about adhesives? We said before that adhesives are a little different than anything else we're going to talk about in this course, because I got the surface contamination problem and I got the problem of surface roughness. And adhesives are a liquid, so they take care of the surface roughness by filling in with a liquid. those mountain peaks, but they don't get rid of the contamination, and therefore they're weaker. You don't get the same types of bonds. You don't get 10,000 or 20,000 pounds per square inch. If you get 5,000 pounds per square inch on adhesive, you're doing well. And more typically, you might get 500 to 1,000 pounds per square inch. So adhesives are lousy for fixing your child's toy where the two parts come together with very little area of contact, okay? So he's got an antenna on his little car and it breaks off, and you can glue it all day long, but it's not going to stay together. If you want that thing to stay together, throw it out and go buy another one for Fisher Price, okay? They just don't stay together because it's low surface energy. We haven't talked about, you got to talk about surface energy at some point. But adhesives are great. So first of all, you need lots of surface area. And that means that simple bonds where I have a small area between two long bulk things is no good. If I have long fibers, like fiberglass, which is basically just glass fibers inside a polymer hot melt adhesive, okay? That's very good. I got lots of surface area on those fibers. Or if I have a bunch of little powders, solid powders, surrounded by something, like asphalt paving, where I got rocks and lots of surface area, it's great, okay? So powders, fibers, sheets, but bulk materials, okay, I didn't put sheets in here. So if I got a thin sheet as opposed to a big thick plate, okay, big thick plates are no good. Thin sheets where I have significant overlap between the sheets. That overlap gives me a fair amount of area. It's not like just trying to bond that antenna, you know, to the child's toy. That's lousy for adhesive. Good overlap with sheets is fine. Lots of area with fibers is fine, and powders are even better. So the geometry of what you're trying to bond makes a big difference. And if you're just trying to put two big hooks of steel or plastic or anything else together, it's lousy. It just doesn't work. They're weak bonds. You just buried the contamination. You haven't done anything to get rid of it. The last thing we'll cover today, which I should have covered actually in the beginning, is wetting. And there's something called Young's equation. Whenever you study wetting of surfaces by a liquid, they always go through Young's equation. I hate it. It's actually a fairly simple equation. I have a surface energy between the solid and the vapor. This is the vapor up here. I got three phases. I got liquid, vapor, and I got a solid substrate. So here's the air up here. Here's my liquid wetting some surface. So I can think this is my glass and drinking cup, or my drinking glass that I'm going to put in the dishwasher, and it's going to get water spots on it. Okay, and I don't like water spots where all the soap dries and leaves little spots on my glass, leaving that little bit of grease there. I want something that's going to cause the liquid to sheet off there and form a thin film, so all that grease that's left on my glass after it comes out of the dishwasher is thin enough that I can't see it. Okay, I don't want it left there as little dried up spots. So I want the liquid to wet the surface, and so I can go and I'll buy Cascade with a wetting agent that will make my glasses sparkle, okay? And all it is something that lowers the interfacial energy between the liquid and the solid. There's an interfacial energy, and we typically talk about these as surface tensions. And this is liquid vapor. So this is, you're going to do an energy balance or a force balance right around this point. And here I have a gamma solid liquid. Okay, so I have three different interfacial energies between the solid and the liquid, and there will be some tension pulling this between the solid and the vapor and between the liquid and the vapor. And if I resolve the forces in the horizontal direction, so this is sort of like even mechanical engineering, right? Solid, gamma solid liquid, for this point to be at equilibrium, must equal gamma solid vapor, which is pulling in the same direction, plus gamma liquid vapor cosine of theta, where this is theta. And all I'm doing is resolving, oops, I did that backwards. Minus, there'll be a minus in here, so. But the way we usually write it is the cosine of theta on this side. So it would be gamma liquid vapor cosine theta plus gamma solid liquid is equal to gamma solid vapor. So solid vapor is pulling in that direction. These two are pulling back in this direction, but this one that's coming up at an angle is only pulling back with cosine of theta. That's Young's equation. Okay? And any time you talk about surface tension and wetting of liquids, someone will, the first thing anybody writes down is Young's equation. This is the last thing I write down. And the reason is, it only applies at equilibrium. And if I'm actually talking about a liquid wetting a surface, I'm not at equilibrium. It's a dynamic situation and I'm not at equilibrium, and Young's equation can't be applied. This is sort of like thermodynamics. You know, if you're talking thermodynamics, you have to wait for equilibrium in order to do your calculation. And so there are people all the time who pull out Young's equation and they forget that it only applies to equilibrium. Okay? The other thing is, the more you study Young's equation, the less you understand it. It's a very simple equation, and everybody thinks they understand it. But if you actually try to apply it in the real world, even when you're at equilibrium, you find it doesn't really work. Okay? Let me give you a simple example. People have tried for years, they'd love to be able to screen print solder. Okay? If I could make a little inkjet printer, and people have, Professor Sonnen over in mechanical engineering was the one that introduced this problem to me. And they like to shoot a little solder ball of solder on it. You can print your circuit board. You can make custom printed circuit boards very quickly. You just print them like you print, off a bubble jet printer. Okay. And I've seen things where in wax people do this, but when you try to go to high surface energy solders, people have not been able to do it. And you run into instabilities, but it turns out Professor Sonnen calls me up one day and he says, I've been trying to apply Young's equation to this geometry of a ball sitting on top of another ball. And it turns out, he says, oh, well, you just apply Young's equation, right? You get the angle of contact here, you do your equilibrium forces, there's your gamma solid vapor or liquid vapor, and here, you look at all these things and you try to apply it and you find that it doesn't work. You end up with the actual surface angles you end up with have nothing to do with Young's equation. And it turns out, without going into all the details, mathematicians have now gotten into this, and part of it has to do with the cylindrical geometry and the fact that I've got like materials here. It's the same material. And so there is no interfacial energy in between here, in theory. And so one of these goes to zero. And it turns out this little concept of Young's equation, everybody wants to use it, but it doesn't work when you actually try to apply it. So we'll talk about Young's equation. However, a lot of people will put a drop on a surface. If you wax your car and rain comes along, you'll see the little beads of water on there. And you measure that angle, and there's lots of industrial tests where they're trying to measure the properties of surfaces, and they will measure the contact angle because it's the easy thing to measure, and they will have it as a go, no-go phenomena for whatever their process is. They don't really know exactly what they're measuring, I guess is my point. But most people say something wets the surface if theta is less than 30 degrees. It's considered a wetting liquid across the surface. If it's more than 30 degrees, you consider that it beads up and the stuff doesn't wet the surface, and you get spots on your glassware when you do your dishes. And you should buy the more expensive Cascade to avoid the spots. Okay. Sorry to run over, but I'll see you Thursday.